The Nuclear Talent Show is a long-format interview podcast hosted by my husband and nuclear engineer, Russell Goff, produced by our staffing company, Nuclear Talent Scout. For more educational and career-boosting content, including exclusive lessons from our talent show guests not included in the show, visit our website, nucleartalentboost.com. You will get access to all of our content, our forum discussion spaces, and membership in an elite talent pool that will shoot you to the front of interview lines. All this and more for free in exchange for your resume and job preferences, which allows us to save you time because we'll only reach out to you about states, rates, and dates that fit your desires, unlike so many other recruiters. We can place you directly in-house with our clients or as a staff aug contractor. You sharing this video with your colleagues could help them obtain life-changing jobs, and it allows us to continue making this amazing content for free. So please like, share, and subscribe to our podcasts, follow us on LinkedIn, and enjoy the show.
So yeah, Chad, Adam and I were talking the other day about how very few people can actually intuit if 30 dB microvolt at 20 megahertz, like a meter a distance away. Is that a ton or a little EMI, and what situations? How does someone go from either knowing nothing about EMC or knowing that you have to follow Reg Guide 1180, but not actually knowing how to follow it? How does someone advance from this childhood into adulthood of EMC? How did you do it? How would you recommend others to?
So you only have to know 2 words. You have to know it depends. As long as you know those 2 words, you can solve any EMC problem.
Any engineering problem.
Any
sure.
engineering problem. So it always depends. One of the biggest challenges with EMC is it brings in all those things that in school they taught you don't worry about. So they said, don't worry about parasitic capacitance. It doesn't mean anything right now. Don't worry about neutral inductance. It doesn't mean anything right now. EMC brings all those things back into play. And so really for me, one of the biggest challenges with EMC is everybody views it as black magic. It's all seen as, well, nobody understands this. You're just waving your hand and you're making things go away. And so one of the biggest challenges is getting people to actually understand that EMC may be a problem and how do you address it. When it comes to handling EMC issues, it's fairly straightforward. You just go through, put some simple design practices in, make sure you wire things up properly, and away you can go. But the biggest one is just understanding and being able to comprehend what EMC actually is. One of the first things that people always try and show me when it comes to EMC issue is a schematic. And the thing I always tell them is, I assume you designed the system properly. EMC doesn't show up on schematics. So it's all those things that you can't really see that's there. And being able to understand that is really the key to understanding what is EMC. And so I always start by giving examples or giving demonstrations of how you actually see EMC occur. So once you can appreciate how EMC can be an issue or how EMC actually is something you should consider, that leads you towards, okay, well, how do I actually address all these different types of things? And that's where you get into the EPRI guide, EPRI TR 102323, and the NRC Reg Guide, and all those different documents.
Nice. Yeah, because often schematics just assume that proper grounding is in place.
Yep.
And it's just a no-brainer. Obviously, it would be there, but it's not.
Yep. Yeah. So the circuit shows a very, very small little grounding node on the schematic. But if you use a 10-foot wire to make that happen, it's no longer going to be a very good ground at that point. Mm-hmm. And ground's another interesting concept. Whenever I give my training courses, there's always 4 myths that I kind of want to go through and dispel. And the belief that ground is the solution for all things EMC related is one of the biggest myths. Ground is not some big sink for noise. Noise does not want to go to the earth. The earth is actually a very, very poor conductor when it comes to EMI. And so you're not going to get noise if you want to go to the earth and just stop there. Dispelling that is one of the big challenges with giving an EMC training course. Again, it's getting people to rethink what it is that they know.
Well, I'm questioning my life already, and I'm an expert, but there's experts in relation to people who are 10 pages in the book behind you, and then versus someone that's actually read all 1,000 pages and done it like yourself.
Yeah.
So I'm very, very humbled to get to talk to you about all these topics. But you noted that it's all the stuff that they don't teach you in school or tell you not to worry about in school. And you probably couldn't tell someone go take electrical engineering 372 at your local college. And so one of the resources that I've found useful, and obviously you have your own training course at AMS, which is by all means the tippy top best thing that you could do and everyone should do. But like for me, it's this little book called the Electromagnetic Compatibility Pocket Guide that Rhodes and Schwartz puts out.
Yeah.
You can just sign up on their website and give them your address and they like mail this to you. And it's got all the basics and fundamentals. It even has LinkedIn groups, Android apps that like it recommends and stuff. It's good reading. Rhodes and Schwartz, we'll put the link in the show notes, but they do a lot of online trainings, mostly free, and it definitely gets your feet wet. Nothing like replaces actually reading those EPRI manuals that you just spoke through. And there's like 4 of them and 10 different revisions of each.
Yeah.
And the revision that you read actually matters a lot. And so we'll try to put you onto the right revision in our show notes here as well. But yeah, is there any other like outside of your training course recommended reading or short videos that like explain some of these concepts for people?
Yeah, as you mentioned, there's a ton of online resources that you can go to. There's several either web series, just websites that will list off and provide various types. For me, one of the best textbooks I've ever read on EMC is actually Henry Ott's Electromagnetic Compatibility. Most textbooks, they're very geared towards, I would say, classroom lectures and being a course textbook, whereas Henry Ott's book is it's easy to read. It's kind of fundamental. It hits things at the level that I need them to be. When it comes to nuclear power plants and doing EMC, we don't worry about board level stuff for the most part. We're taking commercial off the shelf components, or we're taking microprocessor based or FPGA based systems and just implementing them. So I need things at a system level. And most EMC textbooks get to it at a PCB board level. So that's where Henry Ott's book is very good at explaining kind of why you have to do certain types of things. As far as grounding, the IEEE 1050 guide standard is one of the best I've seen with referring to how do you address grounding. It goes through the 5 different reasons for grounding and how do you have to go through and implement optimal grounds. Because one of the challenges is everybody wants to know, okay, come review my system and tell me what I need to do to fix it. And with that, it all depends on what your philosophy you're taking with respect to EMC. Sometimes isolated grounds and isolated instrument grounds and safety grounds being separated are good things. They can solve issues. I'm of the philosophy, I like them all tied together. And so when it comes to, well, what's the right approach? There's not really a right approach. It's does everything build upon your philosophy and your design practices to be able to make that happen? So that's one of the things where you can't kind of backfit how you address EMC to somebody else's design. You kind of have to go in and understand what the design is and then make sure that you're following those same practices to be able to make it happen. Because one of the things I do is I say, don't change anything, because bonding both ends of shield to ground. To me, that's the way to do it. I treat a shield like I treat conduit. But if you do it improperly, you can run into issues. And so I tell everybody, don't go and bond every single end of the shield to ground, because it all depends upon how you've actually implemented your system. So there's a lot of those types of things. And that's one of the challenges with engineers and doing EMC is engineers, everything be black and white. They want this rule applies always. This other rule always applies.
Sure.
And when it comes to EMC, we're in the gray area. Sometimes I add a ferrite bead, it makes things better. Sometimes I add a ferrite bead, it makes things worse. And being able to understand why is really one of the big challenges with EMC.
Yeah, that's definitely where it gets into you can spend 2 hours reading a textbook and reading 1050, but a minute to learn, lifetime a master thing. And certainly why, it behooves everyone to find someone like yourself who's a real expert and pay them to spend 10 hours fixing your problem immediately instead of spending 1,000 hours of your own and ruining your company's schedule and stuff.
Yeah, I'd say one of the funniest things I've had is we qualified a system one time and it failed to meet EMC. And so we fixed it for them. And so the next time they said, well, do this design review for us. Make sure that we're going to be more likely to pass when we get to qualification testing. So we went through, we did a design review, and we said, okay, this one component right here, take it and flip it around so that you basically aren't intermixing inputs and output cables. And they said, yeah, but that's going to affect our sill screening. Now our lettering is going to be upside down, so we don't want to do that. So then they sent it to us to qualify, and it failed. And so we took that one component out, flipped it around, put it back in, and everything passed. And so then they said, oh, well, now we can change the silk screen. So rather than changing all that at the front end of the design when they had time, now it became a rush job. It was all because they didn't really believe us when we said, well, that's going to be a problem. So again, it's understanding when you think about it and you look at it, it all makes common sense. But until you actually worry about these two cables being next to each other, you don't really care about it.
Yeah, that's right. My design spec says it'll meet Reg Guide 1180. Surely the vendor will pull through and meet that. We'll get into this later, right? We'll get over what the CE stamp is and what the FCC stamp is, why that would give you some confidence or whatever. And Yeah, I mean, that's going to be the thing, like reserved for nucleartalentboost.com that like you have to register to like get this ooey
Yep.
gooey
Yep.
delicious insights. You mentioned that you preferred going to the, everything down the single ground path instead of having separate grounds for like separate safety systems and stuff and instruments. And to me, it's just the single point failure, nuclear ears. My ears are hurting
Yep.
hearing that. Why do you prefer that strategy? And what were the issues that you've seen the other way?
Yeah. And so for me,
And it depends.
Yep.
It depends.
Always depends. So I have seen a ton of isolated instrument grounds within plants, and they work. Systems work. And so again, I'm not saying that you want to move away from that, but for me, if I were designing from the ground up, I would have the single point ground because I like everything being referenced to one location or to one EMI reference. That helps me control where all my currents are flowing. And that's really what EMI comes down to, is you control current flow. The more you direct where the currents go, the more you can keep them away from where you don't want them to go. And that's where when designers go to isolated instrument grounds, they're trying to avoid handling those currents. So that's just one of those things where they don't want to deal with it, so they just isolate it. But for me, I'd rather control it because once I control it, I make sure it goes where I want it to go. And that's one of the things. Again, I do a demonstration in my course where I show how just because I bond a cabinet to ground using this big 4-aught ground wire doesn't mean current's going to take that path. Noise current, EMI is a current, and noise currents follow the path of least impedance, not always the path of least resistance.
Yeah, I mean, people are like, it's like the same reasons why like nuclear is so spooky and superstitious to people, right? Radiation is a thing you can't see. And like in the same way, you can't watch the electrons flowing through that copper or whatever. So it's just like all like spooky. Like, what are they actually doing? And like, is stuff waves or particles? And like, why are they even doing this? You can't even tell me that and all this. Like,
it's all just black magic to everybody. So that's where sometimes ferrite beads, I'll take them into plants, I'll put them on cables to try and, because all ferrite beads they're reflective devices. They don't absorb anything, they just reflect to try and help control that current flow. But everybody's like, oh, they brought their prayer beads out now. It's like, oh, well,
things are getting serious. Things are real now.
Yep.
Yeah, like, this is one of those things where it's like there are 3 or 4 other physical things you can do to modify a system to get better at EMC. But like for me, if a ferrite bead doesn't work, it's over. Like, that's the level of my troubleshooting.
Yep.
I pointed this out with Adam, but for anyone only watching this episode, here on this microphone, like I've got the CE stamp, I've got the FCC stamp, and what is this little round thing, Chad? Like,
yeah. What is this little ferrite bead that's on here? Yep. Why?
Yeah, like once you see a ferrite bead pointed out to you that like this is a ferrite bead and this is what it does, you just start seeing them on everything in your house, and you're just like, how was I just this unobservant about my surroundings?
Well, that's funny when you get the cable that has one on each end, and you're like, well, why is there one on each end? It's all because, they don't know which side you're going to plug in. So they have to put one on each end.
Yep. I was actually just looking at such a cord in my house.
Yeah.
So, wow. Beautiful. I mean, the joy and thrills of engineering, right?
Yep.
Learning about the world around you. I'm watching my daughters grow up, right? And they say like, oh, hey, like there's a bird. And it's like, hey, like that is in fact a bird. And then later on, they're just like, hey, that's a bluebird.
Yep.
And it's just like, yes, indeed. And it's just like, that is a northern blue jay. And like, this is like the progression of understanding and like deepening of our knowledge in any field.
Yeah,
doing the same thing in electronics.
It all builds upon itself. So when I started learning EMC, same thing. I took EMC courses, and so my mentor, he would teach these courses, and I would go sit in these courses, and I would pick up about 10%. His first course, I'd pick up about 10%. The second time I saw the course, I'd pick up another 10%. So it took me about 4 or 5 times of going through that course to start to feel like, okay, I'm actually maybe starting to feel like I understand what's going on here. And then once I had to start teaching the courses, now it's okay, I better learn it. And one of the things I hated about it was I kind of started with his course material. And he intentionally put things wrong in the courses because he wanted to point them out as he was giving the course. And so I would start going through his course slides. I'm like, that doesn't make sense. Then eventually I realized, oh, well, that's because he would say these things are always wrong. This certain portion is wrong. So again, it takes time, but you're building upon all this starting knowledge to expand into what you do know. So there is a light at the end of the road.
That is dirty for the professor to do that. And it actually reminds me of a friend of mine recently who is, had the sneaking suspicion that people were just rubber stamping his calcs and stuff when they reviewed him, right? And so he just started writing, like orange unicorn and like more explicit language than that even throughout this 20-page or 200-page document. And then sure enough, the guy like says like, oh yeah, like I hit approve or whatever. Yeah. And it's just like, no, it's like, this guy's clearly not reading my stuff. I'm glad that professor was able to show who was and wasn't at lecture that day.
Yeah. Well, I had another professor one time, so I had an electromagnetics class, and the final exam was 4 questions. And the answer to each question I worked all out was 0, because you had right-hand rule and all this stuff. And so I went through the exam, worked it all out. I was like, all zeros, can't be. So I tried to go through and work it all over again. But sure enough, every single answer, every single question on that exam was 0. I thought that was just kind of
Wow.
cruel.
There's like really, truly like emotional and psychological damage
Yeah.
in when you go through engineering school. Like my dad was like a PhD in like veterinary medicine. That's like his deal. And like he went to Cornell and stuff. And he was just like, hey, man, I survived undergrad at Cornell because I was able to handle that pressure. Like everything else in my life has seemed very
Yeah.
easy. It looks like you went to Tennessee, right?
Oh,
And
yeah.
they've got a pretty strong program. And yeah, I went to Purdue and it's also like a bit of a pressure cooker. It's really true. Like I've always felt that like my day job has been like very easy compared to like professors telling you like, hey, you have to like go design a reactor in 2 weeks. Give me the answer. And it's just like, I have so much time and people are paying me to do this.
Yeah.
Like this is great. One thing I wanted to talk to you about was using marine and aerospace and like military and medical device EMC standards to achieve compliance with, or at least give you pretty good confidence that this widget's going to pass Reg Guide 1180. Is that something where, at least when I've been shopping around for widgets that are going to be suitable for a nuke plant, like I'll look at some of these standards. Is this something that's like common for you to do as well? Or
Yeah, so the first thing you want to always do is when you assemble a system, you want to try and find components that have some sort of pedigree. I call it pedigree. So they should have some sort of EMC pedigree to them. Now, like when it comes to FCC testing, FCC only tests for emissions. So they only measure what comes off of the piece of equipment. They don't look at, well, what can it withstand? They leave that up to the consumer to be able to deal with. Whereas when you get more to the international space, they want to make sure you have some immunity. They want to make sure your system can withstand a certain level of energy. The first thing is always looking for, has this system been tested for anything? Do we have some sort of documentation? And usually that's just going to be some sort of, they're going to list off some standard or some EMC directive. Then you got to kind of dig down into, okay, what's this directive point to, which is a whole mess when you go in the IEC space because they like standards. And so they'll have a standard that will refer to 4 other standards that refers to 10 other standards. So you have to kind of work your way down through those. But yeah, you always want to start with things that have some sort of pedigree behind them. When it comes to the Reg Guide, it's going to be the military standard. So Mil Standard 461 is what's traditionally been used to qualify equipment. In the last couple of years, there's been a little bit more of a shift into the IEC space and using more of the international standards to be able to do that. But like I say, either way, it's acceptable because to me, I don't care as much about, well, does the system make it so that 6 dB below the limit? I want to know, is this thing 30 dB above the limit? So is this thing screaming noise or is it kind of in line with where I want it to be? It's usually how I've treated them. So for me, there's different limits, different requirements between the EPRI guide, the Reg Guide, some of the IEC standards. I'm not as worried about, well, which limits am I trying to meet? Because now we're splitting hairs. I more want to know if I can meet some sort of requirements. It shows that somebody has some forethought to say, let's design this thing with the EMC in mind. So that's usually how I approach things.
Nice. No, that's perfectly good. And let's go further into that. So there's the EU Directive 2004/108/EC, and that's the European Union's thou shalt make your electronic components not scream electromagnetic interference at other electrical devices nearby and cause headaches for everyone. And they also require like, hey, thou shalt be able to receive some amount of this electromagnetic interference and still like go on functioning fine. And as you said, this is different than the FCC, the Federal Communication Commission at the USA, like which is their Part 15 regulations, which the F with like 2C, it's like a very nice like graphic design, the FCC logo. But when you see the FCC logo, that's only saying we will not harm others. We will not emit our own emissions. Does this mean that if something has an FCC stamp, you can't trust it compared to a CE stamp? No, like obviously people that make electronics want to make sure their electronics keep working. So it's just that the regulations and the stamping didn't require them to, whereas in Europe they do.
Yeah, although you have to be careful because you can self-declare a CE stamp. So you can put a CE stamp on something without doing any actual testing. Usually if something has an FCC stamp, it has some sort of FCC report with it. And that's one of the nice things about the FCC is they list those reports on their website. So you can go and you can download that report and see the actual data. Whereas in the IEC space, just because they say they meet a directive or they meet a standard, they don't always want to give you that test report. which if you're trying to take credit for, you really need that test report to be able to have. Along those lines, so the FCC doesn't require immunity testing, but one of the good things about EMC is, so antennas work both ways. They radiate and they receive. And so if you are able to stop your system from emitting frequencies, then maybe you've also prevented it from receiving those same frequencies. So there's a little bit of two-way street there with, if you have good emissions of your system, likely your system may be designed well from an immunity standpoint as well.
That honestly never even clicked with me. That would just be like, you're already 90% there, sort of a two-way thing.
Yeah, as plants want to move and deploy wireless technology, one of the things we always used to do was do basically a site survey. So we go in and passively measure what's in the plant. So we're looking for the frequencies that may compete with wireless technology. And one of the things we're really doing is saying, okay, if we see emissions in the plant that are at the same frequency as a Wi-Fi transmitter, well, that means if it can emit that energy, it can also receive that energy. So therefore, that equipment may potentially be vulnerable to 2.4 gigahertz. So that's how we used to do a lot of the site surveys. It was all passive. Now we go and we actually inject energy onto plant equipment to see what it can withstand. But the approach is there. If you can receive it, you can also radiate it, and vice versa.
Yeah, it is like the CE stamp being a self-certification. I've actually rarely, maybe they actually do have where you can get a third party certifying it instead of the actual manufacturer. Are you aware of that?
So that's where you can send it off and get tested. And then as long as you meet the requirements of the directive, you can put the CE stamp on it. But I think there are some companies out there that will just say, oh, yeah, I looked at it, I reviewed your system, and yeah, you can put the CE stamp to that. Now, I think that's rare for that to happen. So in general, I typically err on the side of believing that they actually did do the testing of that system, but you just have to be careful with that. But so when it comes to like a CE stamp or a CE mark, there's a collection of about 7 different standards that it would kind of require to be performed, which kind of jives with the nuclear requirements in a lot of ways. Just nuclear adds in other things. So when it comes to trying to use a piece of equipment that has a CE stamp or some other EU directive, you can take credit for some of those, but then you have to either test or analyze those other tests that nuclear kind of throws at it as well. But it can be done.
Yeah, and I think like those other tests and stuff, my layman's rule of thumbs is just that like doing the EMI and the RFI like emissions and susceptibility stuff, that's all like sort of somewhat child's play. And like the real thing that's gonna like make your component fail is the surge test and the electrostatic discharge test. And could you speak a little bit to that about how that's just the equivalent of just getting hit with lightning and like that being the thing that like if your spec is demanding it, like, yeah, that's going to be what makes you have a problem? Yeah.
So as you mentioned, in general, EMC is divided into 2 parts. So emissions and immunity. So the EPRI guide, they have those 2 categories. When it comes to the REG guide, they have emissions, immunity, and then surge withstand capability. That was Rev 1. Now in Rev 2, they've added an ESD as a separate aside. So when it comes to immunity, we're talking about high frequency radiated conductive immunity and low frequencies. Most of those tests will cause disruption of signals. They don't cause damage. When it comes to surge withstand capability and ESD testing, that's when you are subjecting the equipment to several thousand volts and you can see the smoke come out of pieces of equipment. And so really I divide it into 3 different things. So one is electrical fast transients or EFTs. So the things that are created by plugging and unplugging something, de-energizing a relay, those types of transients. Those transients can be several thousand volts. One of the experiments I do in my demonstration is I'll cycle a 60 volt relay and I'll create 2000 volts of a transient out of that. Even though it's a high voltage, it doesn't have a lot of current behind it. So energy-wise, it's kind of very small. So electrical fast transients, typically I'll see them kind of destroy memory of systems, but not just completely destroy a system. Now, when it comes to a surge event, so a surge can still be several thousand volts, but it's going to be a lot longer duration. And so that's where there's a lot more energy content behind it. So electrical fast transient lasts for nanoseconds. Surge can last for microseconds. So you're dumping a lot more energy into it. And that's when you can really get the smoke come out of the system. Now, when it comes to surges, they're fairly easy to handle. Surge suppression, as long as it's properly installed, you can handle most surges. So it's not that terrible to address. But from a test lab standpoint, we'd like to see those things blow up because it's just fun for our engineers to see and have that happen. But
sure.
Probably the most destructive EMC test is ESD. So ESD event,
which is electrostatic discharge.
Yep.
ESD, electrostatic discharge.
And everybody has experienced that. They've been walking around the house on the carpet, go and touch a doorknob, and you get that shock. So again, that shock is very low energy, so it doesn't kill us, luckily.
It's just annoying to your siblings, but like when you are sitting next to a bunch of FPGAs,
Yep.
yeah,
Yeah.
it's good.
Electronics do not like it at all. And the reason is because your body can store up tens of thousands of volts. So the test is 15,000 volts that you can store in your body and then discharge. Again, very, very low current, but that high voltage can really mess with electronics. It's high voltage and it's very, very fast rise time. You're on the order of picoseconds or hundreds of picoseconds. And high frequencies couple very well. And so that means it's very, very tough to protect against DSD. So those two things, being very high voltage, coupling well, and being very difficult to protect against, make it very, very destructive. So that's where we usually save ESD testing for last. So we kind of say, okay, let's test everything else, and then we'll hit it with ESD and see what happens.
Nice. If you're pulling out some cards and like trying to like do maintenance or whatever, you'll just have those wristbands that like help be like anti-static, and like you might have to wear like anti-static clothes and stuff, but like despite what you do and whatever, like a squirrel on a dry winter day when your HVAC system's a little out of whack is just going to end up making a little zap, and you got to make sure that you can deal.
I've heard of some plants putting in like ESD carpet or humidifying the room. So lots of humidity, you can't store charge. So that's why during the summertime, you don't really have very many issues with DSD.
And you could have such a silly licensing basis that you're just going to be like, hey, we've got like this safety related humidifier that also doesn't get it too wet. Or you can just do the qualifications and throw in the suppression stuff and like off you go. Hence why you exist.
Exactly.
Hence why we value you, Chad. And everything that AMS brings to the table. Yeah, Adam and I already had talked to this one where, Reg Guide 1180 is historical averages in plants or like what was bounding back in the day. And your new reactor design might not actually be bounded by it. But I think the other thing is that, especially if you're trying to go to like non-nuclear vendors, and even nuclear vendors, honestly, will sometimes struggle with what does Reg Guide 1180 really mean? It's often better to like in your specification to just copy paste a segment of the tables from it and just say like, here's the levels, here's half a page, exactly what you must withstand and meet, because it's just lame to send a non-nuclear vendor the 40-page Reg Guide 1180 with all its optional paths that the designer and like ultimate architect has to decide which path they're going to allow. Yeah, it's just lame compared to actually writing a good spec. Do you want to speak to how to write specs that don't suck and don't offend your vendor?
Yeah, so one of the worst, or what I've seen a vendor do before is in the requirements from the plan, it says, thou shalt test the system for the test in Reg Guide. And the vendor took that as, well, they just said test it. They didn't say we have to meet it. It just says you have to test it. So we don't care what the results are. We just want you to subject it to these tests. The critical thing is making sure you say what you want the system to do. So as you pointed out, actually listen up. We want you to do this test, this test, this test, and what the test levels are. That's really what's going to provide value to your spec so that your vendor that's providing that system knows exactly what it is that they have to meet. Again, I've also seen where it says your system shall be able to withstand EMI or RFI. But again, okay, what does that mean exactly?
Thou shalt not emit EMI, period.
Yeah, so
it's like unactionable. You want
to... so that's one of those things where the EPRI guide has an example purchasing spec in there that says, okay, for your systems, whether it's safety related, whether it's important to power production, whether it's non-safety related, you're going to do these certain types of tests. So yeah, definitely make sure that your spec is appropriate is kind of where you want to be, and make sure you update it. So as these requirements change, updating your spec, because that's another thing I've seen where a spec, it endorses the latest revision of the EPRI guide, but they didn't update their requirements for tests. Well, those tests actually changed. And so they're saying, well, we EPRI Rev 4.
Yeah, that's right.
So have somebody kind of review what's your purchasing spec look like to be able to make this happen.
Yeah, that's right. Because indeed, and I've never actually encountered it where it actually made a difference. Because usually, like someone who's done the testing to Rev 1 of Reg Guide 1180, like happens to have also met Reg Guide 1180 Rev 2 levels.
Yep.
But theoretically, that gap does exist and like could actually. So you have to actually check it every time if it's an old qual. And for some reason, you've decided that the new revision is absolutely what must be met, which Also, at the end of the day, like Reg Guide 1180 is giving like a spectrum of what would be bounding. And in my opinion, whether you're quote unquote committed to Reg Guide 1180 or not, at the end of the day, if you just had a one-on-one conversation with any member of the NRC staff, if you can prove that your environment out in the plant is this, and what you tested to is better than that, even if it's not meeting Reg Ed 1180, it's like that, this is fine.
And the other thing is as the requester, knowing that your responsibility doesn't end just by saying you have to meet the requirements of whatever. Because one of the big things during immunity testing is you have acceptance criteria. So your system has to perform in some sort of manner as it's doing the testing, and that acceptance comes from you. You have to say, well, how much can this 4 to 20 milliamp signal deviate? Or can my screen flicker during testing? So you're the one that has to tell the vendor or the provider of the equipment how that system has to perform while it's being subjected to that testing. Because what I often hear is, oh, well, the acceptance criteria, well, that's in the reg guide or that's in the EPRI guide. It's like, no, that does not include any of that information because that's all site specific. And that's where I'm leery of generically qualifying equipment, because a generic qual means that however they tested that has to apply to every single system, every single use case for this system. And that just doesn't always apply. I was doing testing for a system one time, and they sent it to us because it was failing EMC, and they said, well, fix it. So we got the system in, and it was like a little recorder, like a digital recorder. And so we said, okay, rather than using this 1 foot ground wire to connect your recorder to ground, use a 1 foot braided ground strap. Use that and you'll pass this test. And they came back and said, yeah, but our closest ground is 8 feet away. I was like, well, then why are we having us use a 1 foot drain wire for that? Well, that's how it was generically qualified. It's like, yeah, but if that's not how it's going to be used in the plant, you can't use that. So then we had to come up with a whole different solution for it. So that's where, like I say, be very, very leery. So if you're going to try and use a generic qual, make sure you understand how that system was tested, how it was set up, and how it performed during that testing.
Chad, you just speak to my heart, and we have the same wounds, and I love it. If I had $1 for every time I heard someone on a new reactor or like a new project, or even just like a plant upgrade, say, oh, well, we don't have to design anything new. Like, we're just going to use pre-qualified equipment. And we don't even need to have an equipment qualification guy around because it's just like the vendor's already done all this. And it's just like, yeah, like there's actually a lot more to it than that. It's great.
Well, and so one of the other things about the Reg Guide and EPRI Guide, they were developed based upon what the plants looked like, what the new commercial nuclear power plants looked like back in the 90s. And so they went and did a bunch of measurements in the plants and said, okay, this is kind of what a plant looks like. Let's develop our EMC qualification levels based upon that. So that's one of those challenges of, well, does that apply to advanced reactors? Does that apply to field processing facilities? What type of facilities that actually apply to? But the other approach they have traditionally used has been, we want to have one test level. So no matter what the equipment is, no matter where it's going in the plant, we're going to qualify it to this one level. So they tried to find what's the most conservative level we can use to test to. And they've been doing that approach for the last 25, 30 years. There's a new push, kind of, I did this in the IEC standard for EMC of nuclear power plants, and EPRI's kind of taken a similar approach of saying, okay, rather than qualifying it to be used anywhere in the plant, let's qualify for where it's going into the plant. So actually qualifying it based on what's the environment it's going into. So that's where there's kind of a new approach that's being used, which is good in some ways because now you don't necessarily have to over-design your system to be able to meet some of these harsher EMC requirements, but it also comes with a challenge because now you have to be able to look at your environment and determine what type of surge environment do I have? What type of RF energy do I have? What type of ESD environment do I have? And that's where being able to do that type of evaluation is not trivial by any means.
There's the cost of actually doing the testing, right? And then there's the likelihood that it's just going to make your design look that much more wonky, or that whatever you design is just going to fail. Like if, you know, you're testing to a higher level. But then there's the trade-off of, well, at least you just quote unquote know that the NRC is going to buy off on it. But again, we keep saying that like Reg Guide 1180 might not be bounding if you just have this component licking some switchgear or like whatever silly routing you might decide to do or placement. And I am a little bit intrigued in terms of the economics and the pro con of doing that location specific survey, because, you have to justify the survey that you did in the plant. And again, for an advanced reactor, what we think will be in the plant at that location, right? There's the cost of actually doing that survey, which I don't know if that's $5,000 and someone walking out with a handheld meter, or like someone setting up a whole big rig and it being a 4-day campaign. But when I'm done with my rant, you can speak to these things. But you have to convince NRC that like that survey was indeed bounding, and some transient EMI source isn't going to just wander through there like with a walkie-talkie.
Yep.
And then the cost of fighting the NRC to prove that, the cost of actually doing that on-site survey versus the cost of just qualifying it to those probably more conservative Reg Guide 1180, sometimes overkill Reg Guide 1180 levels. And I think that the compromise that I've seen sometimes is that you can get to the point where you can at least argue why the ESD isn't needed, and that's the toughest test. And if you can at least get that far, it can sometimes be worth it. But please speak. The stage is yours.
No problem. So the Reg Guide actually does, it lists in there, you can adapt your test levels based on what the environment looks like. So it's written into their Reg Guide that it's allowed to do it. They don't really tell you how to do that, but it at least tells you that you can do it. The other thing that's in there is they say it's upon you to make sure that your environment's kind of bounded by what's in the Reg Guide. So at least part of your EMC package should be, if I'm going to use the Reg Guide, my environment is bounded by the Reg Guide because of X, Y, and Z. So you should at least have some sort of evaluation that you've done to say, yep, my environment looks like what they expect to have in the Reg Guide. If you want to be able to go and evaluate what your environment looks like, as you mentioned, you can go in and you can measure it. You can go and measure what's out here in my environment. That can take you anywhere from an hour per location to 2 weeks per location. It all depends on how extensive you want to go into that. You want to be able to ascertain, okay, what's my environment look like? What type of EMI do I have here? What do I have to protect against? And that's where there's an IEEE standard, IEEE 603. They have an appendix kind of devoted to EMC. It's not that extensive, but it lays out a plan that I really, really like for addressing EMI. And that is, they say, okay, one, know what your environment is. So either go out there and measure it, or do some sort of analysis, some sort of evaluation, say, this is what type of EMI I expect to see within this environment. And two is understand, what does that EMI look like? How is that EMI going to be able to get to my system? So looking at how's the cabling going to be installed? Where's my system going to be located? Do I expect to see more capacitive coupling or more inductive coupling? So understand, how is it that EMI from this environment can get to my system, and then design for it. So add in shielding, add in grounding, add in software error correction coding, retransmission. Add all these things in your system to design for that type of EMI, and then test to make sure you actually met it. So those four things that standard kind of encompasses and says, this is the approach that you want to use. I like that approach. Rather than waiting till you get the qualification test and crossing your fingers and saying, well, I hope it passes, that's going to set yourself up for success from the start. And that's where, if you don't know how to evaluate the environment, again, there's resources and tools that are out there. I try to put some of that into the IEC 62003 standard. There's an appendix B and C that kind of covers how do you evaluate your environment and what aspects of the environment lead into these different types of qualification tests. But I say, trying to do that evaluation, it can be challenging at times.
So that was you put that in there, that IEC standard, huh?
Yeah, so it was
talking to the guy that wrote the book, man.
Well, so I revised the book. It was written back in the 2009 timeframe, but I've tried to expand upon that to, again, allow you to do these custom levels when you want to.
Nice.
But it was a group effort. So.
Well, yeah, it's always a trial by committee, right? Yeah, I think that one thing that I'm honestly very interested to hear your take on is that, I've seen electric vehicle companies and, some other industries use 3D modeling and like computer analysis to like be predicting what the EMC levels are going to be in this circuit, or like maybe even in the larger, like using COMSOL or something to like get the general, what's this motor going to be putting out, sort of a rough ballparks of estimates. That's something that like I've almost never seen, or like very, very rarely see a nuclear company or designer using tools like this. Do you think there's a future future for tools like this in nuclear? Are you aware of them being used?
So I'm not aware of them being used in nuclear. I've used some of the analysis or XFTD. I've used some of those types. I've not used any of those types of tools in my day-to-day job now. And part of the reason is there's a lot of information you need to be able to make an accurate model for that. If you don't have everything there, then it comes into, well, how valid is that actual model? So I think some of those other industries, they're looking at the same type of thing. Okay, so we're going to develop this car and it's going to be similar to this other one. And we're going to go through and try and analyze and model what's going to happen here. And they have that down to a lot of very fine design. Nuclear power plants don't necessarily have that level of detail. So one, no two plants are the same, at least not here in the States for the most part. And two, knowing, okay, where's my cabinet at? What type of material is the cabinet? What's in this wall? What type of rebar? What's my spacing of the rebar? So a lot of those things would have to be programmed into the software in order to give you a really good model for that. And that's just where that level of detail isn't there. Could we get there? Maybe. I know some plants are going through and doing basically these 3D scans of the control room with laser technology and getting fine details of what's going to be there. So maybe in the future. But the only way I've kind of seen that used is as they deploy wireless technology. So if they want to know, well, where do I need to put all these access points? So they can go through and place access points on a rough drawing and kind of, okay, what type of coverage do I expect to see? But from an EMI standpoint, I've not seen a lot of that just yet. And I don't see that for the next 5 or 10 years. I don't see that moving its way into there. And part of that is also because the experts on the EMC aspect usually be in the test labs. The vendors don't want to give them a whole lot of information on their system. They're not going to give them, well, here's all these detailed drawings and everything of the system because it's all proprietary to them. So that's one of the other aspects to it.
Yeah, I think that it also gets into the, I don't know, just to give some ribs on the lab rats, right? It's like, this is a technique that some PhDs off in a lab somewhere are doing, but like us real practical blue collar, the nuclear workers, we're just like, I don't know, man, let's just guess and check it. And I don't know, man, is it that hard to like charge this up and just see what happens?
So you also have, there's a group of people that they're like, well, EMC testing, it's useless because if you have a digital system, you are never going to be able to test all the functionality of that digital system. You may only be able to test 0.2% of the functionality or the states that digital system could have during the qualification testing. And the other one is when you do qualification testing, you hit it with one type of EMI at a time. So I hit it with the surge event. Well, what happens if I hit it a surge event at the same time I hit it with a walkie-talkie? Or at the same time somebody touches something and keys a radio because they're talking. So there's a bunch of different things that you can do. And I can make an EMC test regime that takes years to get through. This is what their argument is saying, hey, you're never going to be able to test it enough to give yourself assurance that this state-related system is going to do its function. And there's some validity to that. So they're not necessarily naysayers of EMC testing. They're just saying you better make sure you design your system. So they go through a bunch of different design documents or a bunch of different design aspects that you should incorporate into your system. Because again, they want to make sure that you have a good system going out there. So even if you don't test it, at least you have some good things in place. My approach or my mentality is I may only test for that 2% of it, but it's going to at least give me a feel good for, well, am I really, really bad or am I somewhat good?
Yeah, no, I mean, it gets into like reasonable assurance, right? Knowing the rest of the design of your plant, what this widget must do in what scenario, obviously the redundancies and defense in depth and crediting stuff. You were speaking earlier about how you need to like actually say, got a 4 to 20 milliamp instrument and it's hit with this EMI storm or whatever. And, is it cool if that instrument's accuracy goes from like 2% to like 20% accurate at that point? Are these acceptable tolerances that'll help you get past the test? And then you just have the rest of your safety and operating and procedure basis revolving around these things instead of, this is why nuclear runs away and is expensive. One of the many reasons is that people just will not put in the thought work, either out of ignorance or laziness or just human frailty. It gets overlooked, right? And so you just end up with the design engineers and stuff are like sending to the vendors and to the test labs. It is the difference between American democracy and like a habitable planet even existing, whether or not this particular instrument, while getting hit by an ESD discharge in an earthquake while boric acid is spraying on it, it needs to be within this 0.05% accuracy during all of that. And then everyone just goes and designs and tests and does everything overboard to achieve that, when it was all sort of silly because there were so many other layers of defense and it could have easily had a higher tolerance.
One of the other things I've heard about a little bit more in the more recent past has been geostorms and HEMP. So our nuclear power plants going to be able to withstand these types of events? Solar flares, are we going to be able to withstand solar flares? My stance has usually been, number one, the safety systems of the plant are going to be buried deep down in the plant. It's in concrete, steel structures, so most likely those systems are going to be okay and not be affected. But some of your other ancillary systems, you're not going to need to keep your plant online during those events because most likely the grid's going to go away anyway. So you're going to have no place to put the power that you have because those other things have been taken out. So as long as your plant, the safety systems can withstand it, you don't have to worry about, well, can my turbine withstand it? Because the energy is going to have nowhere to go. So
yeah,
there's a group, I think they've been looking a little bit at, okay, well, what's the effects of HEMP on nuclear power plants and how do we design and protect against them? So
yeah. What was that acronym? Because I think one of them was just the enemies of freedom with an electromagnetic pulse device from Call of Duty and warheads and stuff. That's one. But then the other one was solar flares. And then you just said some other acronym.
Oh, so one is either high altitude electromagnetic pulse or just high energy electromagnetic pulse. But the other one, like the geostorms, is the interesting one. I got a call one time saying, hey, we had this event occur in our plant. There was a solar flare a day or two before. Do you think that could have caused our issues with that? And so it's having to go through that analysis of saying, okay, where is it located? Okay, it's in the bottom of the plant, inside the plant. Do any cables go outside? No cables go outside. Okay, so most likely this is not a solar flare type of event.
Just Jerry walking around with a walkie-talkie again.
Yep, exactly.
Right up the CR. So yeah, you'd mentioned the IEEE 603 appendix that had the EMC section, and we went back to look at it, and it was not actually there. They just change these codes every year.
Yeah, and so somewhere along the way, they took that portion of, I guess, the EMC appendix out. But they're going to try and rely upon P2425 to handle that, which P2425 is going through the approval process. It hasn't gone to ballot yet, but hopefully it'll go to ballot by the end of the year. But that one's more just about how to actually qualify the equipment and not so much how to actually design for EMC. So they're kind of going to be missing a gap there because the appendix of 603 said, hey, define the environment, figure out what type of EMI you have to worry about, design for that, and then test for it. And 2425 is just how to actually do the testing. So it's going to be a little bit of a gap there.
Nice. Yeah, we'll put in the show notes the edition that actually has that appendix and people can go look it up. Is fiber optic cable vulnerable to EMI RFI, or is it just superfluous to say like this fiber optic cable should be
immune? So the fiber optic cable itself will not carry any EMI. You can pass that through a very electrically noisy environment and it's not going to pick up anything. Unless you are, I have seen some plants use armored fiber optic cable before. So it's basically a shield, metallic shield that's over the fiber optic cable. That shield was there basically to prevent rats from chewing through the cable. So they had other issues going on. But by doing that, by adding that metallic cover over the fiber optic cable, now they are introducing a vulnerability to EMI. Because now that cable can pick up noise on the shield and carry it across or through the plant. You don't have to worry about fiber optic cable unless it's shielded or has some sort of metallic conductor with it.
That's the art of engineering.
Oh, yeah,
pick your
exactly.
poison.
But I was going to mention, because we talked a little bit about P2425. So it's a document that's currently under development. It's going to very much parallel the NRC Regulatory Guide 1.180. A lot of the same type of guidance, a lot of the same type of limits are going to be common between those two. It's also meant to kind of parallel the IEC 62003. So I worked on 62003, and the latest version, that's 2020 version. That just covers the IEC path to how to qualify equipment for nuclear power plants. Whereas the IEEE P2425 is going to have both the IEC path and that mill standard path. That's also recommended by the NRC Reg Guide. So it's meant to hopefully eventually be a coverall so that rather than the NRC having their own guidance document for how to handle EMC, the NRC just says, hey, go file this IEEE standard. Or go file this IEC standard.
You know, obviously Reg Guide 1.180 offers like, hey, either qualify it to the mill standard or use the IEC standard. And I've seen it some ways where people will just feel really gung-ho about, let's force all of our vendors to use the IEC path, or like, let's force all our vendors to take the mill standard path. Do you think one path is better than the other, or is it just shooting yourself in the foot to demand a vendor take one path to the other?
So I wouldn't necessarily say that one is better than the other. There are definitely portions of one route that kind of makes it easier for a vendor to pass certain aspects than the other route. However, I wouldn't recommend going and saying, well, I'm going to pick and choose between the two. I usually would leave that up to your test lab, how they're going to actually perform the test, because sometimes it may change based on the type of system that you have, as far as whether you want to go a certain path or not. There are certain things, particularly when it comes to surge testing of signal lines, where the IEC path is much, much harsher for a system to pass than the mil standard path. And typically, we don't see those types of surge events on I/O cables. So in some cases, you're going to be overqualifying equipment. That's going to make it very difficult to either pass the test or you're going to damage some equipment during testing. So in general, I don't like to pick and choose paths because the approach is the same. The intent is the same. You want to verify that this system can withstand EMI. Now, which path you take to make that happen, I'm not as concerned about. But if you dig down into the nitty-gritty details, there are certain aspects of some of the tests that make them more difficult to pass. So rather than saying, nope, I'm always going to do IEC or I'm always going to do mil standard, it kind of comes down to a system by system approach. As a vendor and as a plant, work with the test lab to come up with, okay, this is the approach or this is the type of path that we want to use for this particular piece of equipment. Sometimes if you have cables bonded at one end or two ends, it's going to change how you approach the testing. The type of system, whether it's a very sensitive pressure transmitter or if it's a big inverter, you may approach those types of tests differently. So that's where you may want to tailor how you're going to approach a system based on the system itself, rather than just, oh, well, IEC is always better or mil standard is always better.
That's beautiful, sound, prudent advice, and I'm glad I just have it recorded for all the unbelievers. You'd mentioned I/O cables, which is cables that are carrying a 4 to 20 milliamp signal or a 0 to 10 volt signal of like instruments themselves, and this is like distinguished from a power cable carrying like however many load of current or whatever. So just for the listeners,
that comes down to another point. A lot of times, a system may have 120 volt AC going into it. Well, that may be going to a relay. It may just be a wetting voltage for a relay. And so that 120 volt power cable or 120 volt cable, even though it's 120 volt AC power, it's not necessarily a power input cable to that system. It's more just a signal cable to that system. Same thing, 4 to 20 milliamp loop signal. It's technically the power cable to that transmitter if you're just testing the transmitter. So how you approach treating that, do you treat that as a power cable or do you treat that as a signal cable? And again, it may come down to different approaches for different users. A lot of times I may say, well, if you can protect that cable and it's coming from a DC power supply that's in the cabinet and it's not going to be able to couple all kinds of noise to it, then you may be able to treat that just as a signal cable, even though it's technically a power cable to that transmitter. So how you approach it and how you design and implement things really makes a big play into how you're actually going to qualify a piece of equipment.
No, that's awesome. And I think that one other thing to note is that we just have had our blinders on to this one particular IEC standard and mil standard that are within and cited in Reg Guide 1180. However, if you're out there on the streets just looking for a widget that does really good at EMC but doesn't have that particular sticker, there's a handful of other aerospace and automotive and medical related EMC standards that, if you see that sticker, you can like more or less gold star assume that this is going to be pretty solid. If you felt like you had to, like, would have a high probability of passing the same Reg Guide 1180 testing. And so just to quickly rattle some of those off, the DO 160, SAE ARP5412B, SAE 5416A, which is all aerospace. And then in automotive, we have SAE J1113. And then medical field, they've got IEC 60601-1-2. And this will all make more sense when you just see it in the show notes.
Within the IEEE community, they have an EMC society. So they have a symposium every single year. And a big portion of that symposium, there's a lot of automotive that's there. So there's a lot of work and I would say research and testing that goes into developing and enhancing these standards to a much higher detail. Military obviously has a big presence there. Medical has a big presence. And so to me, the goal of EMC qualification testing is to make sure that you've at least considered EMC in your design. No matter what type of standards you're trying to meet or what type of EMC directive you're trying to meet, if you've thought about EMC, then likely you're going to be better off than I'm just pulling something off the shelf and going to go put it in. Outside of nuclear space, there's a lot of other entities that are addressing and dealing with EMC when it comes to that. And same thing. Mm-hmm. So the P2425 standard that's being developed by the Nuclear Power Society, which, like I say, doesn't have a whole lot of experts in EMC. They have basically a liaison with the IEEE EMC Society. It's trying to still harmonize and not kind of develop something that's off around their own.
Yeah, I think that the same question I posed to you earlier about the fiber optic cables just being inherently immune, similar question for 4-wire RTDs. We can split hairs on a 3-wire RTD and like whether the transmitter itself, but just like let's start up from the most immune, a 4-wire RTD that's plugged straight into your control system. Do I ever have to worry about EMC on that?
So the classic EMC answer is always it depends. So from the standpoint of is EMI going to affect that 4-wire RTD? It's not. It's just a passive device. You're not going to cause a change in temperature that RTD is indicating because you are hitting it with EMI. Now, that being said, if you put noise onto that cable that connects to your control system, that's when you can have the issue. And so it's more about what that RTD is connected to, more so than is this RTD itself vulnerable. That's where does it make sense to say, I'm going to go and qualify an RTD? Not necessarily. Or because we get the same thing with penetrations. If you have a cable penetration, well, we want to get it EMC tested. Okay, well, what are you doing? Because that's just a passive component, a passive device. And so trying to qualify an RTD from an EMI standpoint or a heater, just some inductor or some motor, it doesn't make a whole lot of sense from an EMC standpoint. But how you design and implement that is where that really comes into play. Even a cable penetration, I can hit a cable penetration with the surge, but what am I checking for? The types of tests we would do on that would be to say, okay, can noise get into this penetration? So the way that they bond the shield at the penetration, are you going to allow noise to get into it? Whether it's a high frequency noise, a low frequency noise, a surge current, an electrical fast transient. Those types of tests can be done, but traditionally you would qualify that kind of as a system rather than as individual components.
So I don't know, just for people's context, an electrical penetration assembly, it's maybe like a metal to glass seal and you've got a metal conduit running through it. And then you plug stuff into this end of the tail of the conduit. And then you go to the other side of containment and you plug another wire into those tails. So this is like what we're talking about.
It boils down to it's basically a section of cable, pretty much.
Yeah, it's a section of cable. And again, it's just like, should I say that my cable is EMI RFI qualified? It depends on what it's plugged into. Great. I think something that we've not like actually made the connection to, but that people should know for background is that your surge withstand capability relates to lightning induced transients, right? And so whether your facility is in Oklahoma versus somewhere in the desert where they don't ever have lightning storms would make a difference. In addition to, there's this thing called Regulatory Guide 1.204. And it's essentially a lightning protection standards. It's got stuff like, hey, make sure your lightning protection system is inspected manually and like make sure all the screws are tightened down 3 times a year sorts of stuff. It's just sort of assumed that you already have a lightning protection system and like are considering that in your design, which I don't know if maybe some of these micro reactor vendors that are just a reactor in a semi truck freight container, what they would do for lightning protection, but things to consider.
Yeah, and there's 2 main concerns you have to have for lightning. One is the direct strike. And so that is what all the lightning protection systems are meant for, is if your facility gets struck somewhere, you have a way to divert that current and know where that current's flowing, in essence, back to ground. But it's all about that current control, making sure that you keep the current flowing where you want it to flow. And that's always going to be kind of on the outside surface, outside portions of the building. So it's not going through the building where it can couple. And that's where traditional design says, well, keep any sensitive cable in the plant away from exterior walls, just so that that noise can't couple. The other type of concern is what we call this return to earth phenomenon. So the Sequoia plant back in the 2010-ish timeframe, they had a trip because lightning struck nearby the plant. And so it didn't strike the plant, it never hit the actual lightning protection system, but it struck nearby the plant. And what happened was when that occurred, so as a lightning cloud comes over, it charges up your whole entire facility. When lightning strikes somewhere, all that charge goes away. So everything in your plant had charged up to a certain voltage potential because this cloud that was overhead was kind of repelling charges. So when that charge goes away in the cloud, now everything in the plant has to rush back to some equal potential. In their case, the high side of the conductor on the power supply and the low side of the conductor on the power supply returned at different rates because the low side's grounded, high side's not. And so when that happened, now you have this very large voltage potential between those two, caused an arc to occur, and basically shorted out that power supply. That power supply controlled their rod drive mechanisms and basically allowed their rods to fall in the reactor. That's one of those return to earth phenomenons where no direct lightning strike occurred, but the symptoms of lightning cause these issues to occur. I saw this at another site over in Slovenia. I actually went over there for a WANO mission, and they had no direct lightning strikes. But over the last 5 to 10 years, they started seeing more equipment failures. They could correlate equipment failures with lightning storms. What they had done is, because they had to put it in this new emergency control room, they ran a bunch of cables from inside the plant over outside the plant to this emergency control room. And when they did that, they exposed the plant to vulnerabilities because of this return to earth phenomenon. And so how you design those things really comes into play. Direct lightning strikes, I wouldn't say they're easy to address, but it's more intuitive of how do you address it. The return to earth stuff is not so intuitive.
I think that touches on the concept too of, it's often when you try to make it even safer and add an extra thing that you introduce the vulnerability that actually makes it less safe. And I think lots of people at NRC are starting to realize that and have that in mind. But, it's something that you should always, as the design engineer, also bear in mind. Let's start burning into some of these really nitty gritty distinctions as you wander through the FCC and CE standards.
You'll see the CE mark on everything. I think this thing in here in the office probably has a CE stamp on it. And nothing with that was related to EMC qualification testing. It's just in Europe, they always have to meet all kinds of different directives. And as long as you meet certain directives, you can put the CE mark stamp on something. So that's one of those things where just because it has a CE mark stamp doesn't necessarily mean it's been tested or been qualified for EMC. So you always have to kind of dig down into the details for what those actually are and what was done.
Yeah, you'll definitely see the CE mark on Happy Meal toys and stuff. And it is just saying, hey, if there's any European regulator looking, we are meeting all your laws, whether that's hazardous materials laws or whatever. EMC is just one of a bajillion European laws.
Well, so the Electric Power Research Institute, EPRI, they're currently working on a project to evaluate all the different types of directives or certification bodies across the world to look at, okay, what does the US require through FCC? What does Europe require through the CE mark? What does China require? What does Korea require? What does Japan require? As far as, I'm going to call them the directives, and what do those actually mean? And can you basically use those directives or meeting those directives to say, well, it's good to install into a nuclear power plant? And I think what they're coming across is identifying that while some of the qualification tests are covered by the nuclear requirements in those other directives, if you don't have that test report or access to that test report, you don't really know what it was qualified to, how it performed. And so that makes it a little bit challenging to say, yes, I meet the recommendations of this REG guide based upon this other directive. So for me, it's always, if you're going to use a component, try and get that access to that test report if you can from the manufacturer.
Excellent. In nuclear land, we're just hyper focused on 10 CFR, the Code of Federal Regulations, 10 CFR. But there's other CFRs out there, as we've discussed in other episodes. And so 47 CFR is where the FCC, the Federal Communications Commission, does all their stuff. And so 47 CFR 15 is what on the streets is referred to like Part 15 compliance. And you'll see on the back of your remote control or something, it'll say either just the FCC logo or, meets Part 15 Class B or something like that. And I think that as people are shopping around and you're looking at FCC reports and you're looking at spec sheets that say certain FCC compliances, it's sort of counterintuitive, and you must keep in mind that Class A is the industrial strength, the industrial focused ones, and it's actually less stringent than the commercial strength Class B residential standards, because you go down to Home Depot or something and you want the industrial strength version, right? Because my stain is really huge and I need the industrial strength. But the residential is actually more stringent. And this is because I guess they expect that a design engineer is going to realize that EMC is a thing and that they need to account for it, and that they'll just have technicians around to mess with it. And so they allow your widgets to emit a bit more or whatever, but they do not trust the American consumer in their home to keep their Xbox cords away from their air mattress pump and stuff like that. And that's why you want the residential version of the FCC standards.
Yes. So from an FCC standpoint, they make you control what's going into your house a lot more than what's going into a factory somewhere. But the big thing to remember for the FCC is they only look at emissions. And so they only make sure that your system doesn't put off more energy than desired. They kind of leave it up to you as the manufacturer to make sure you can withstand whatever's out there in the environment. So from an immunity standpoint, the FCC does not have any immunity requirements. The other thing to realize is most of the Part 15 stuff applies to the unlicensed transmitters. If you want to sell a remote or a Wi-Fi device or something using one of the ISM bands. That's where that would fall into. There's also licensed transmitters that may not necessarily have been tested to some of those Part 15 of the FCC. They're going to be tested or certified to different parts 47. Because I ran into that with a site that was looking to upgrade their radio system, and they were going to a licensed transmitter. So they had no FCC Part 15 testing. They had more like Part 2, I think is what they had. Then becomes, well, what does Part 2 say? What are the limits there? What are the requirements? Like I say, understanding how all those different things play into each other is sometimes a little challenging. It's not as challenging. So on the IC side, there's a lot more spider web of standards that go on. In the US, the FCC is a little bit more straightforward, but everyone likes confusion.
Oh, yes. We're about to explore some of that
Yeah.
spider web. But first, on a brief tangent, we had spoken to Reg Guide 1180 offers the mill standard path or the IEC path. And for the reader's awareness, there is this new reg/CR 6782, and it gives this very detailed comparison of the American versus the international EMC standard, that mill standard versus the IEC one. And that's a good resource for people to check out. All this talk about all these committees and, people above the common man writing these papers and forcing us to do stuff. It's definitely like a full-time job to like keep up with all the revisions and even just know who's who and who's doing what and who's having what authority. So I think just a brief overview that I'll read out here and that you can correct or add into is that CISPR, which is CISPR, they are an IEC committee that makes several of these standards. And another term to know is European norms, also known as capital EN. And it's kind of like ENs are like the European version of our Code of Federal Regulations. So whereas we have 10 CFR 55A, as sort of like the place where standards go to get codified into law and then everyone has to follow it. European norms is a sort of like the equivalent. And yeah, just a quick reminder to our listeners that there is actually a difference between a code and a standard. People will just use code and standard as synonyms and like loosely say one or the other for any situation. And that's usually fine, right? We're all adults here and aren't too much of sticklers. But technically speaking, a standard is just a thing that some people threw together, and it becomes a code when it is codified into the Code of Federal Regulations by being incorporated by reference, essentially. And in the nuclear industry, basically, if it ends up on 10 CFR 55A listed there, it's now a code. It's been elevated from life as a standard to life as a code. And so anyway, the CISPR 22 standard document that committee makes is the same as the European norm 55022 EN 55022. I think the thing to note to people is that you'll look up Reg Guide 1180 and it will say, hey, IEC 61000, you need equipment that's passed all that testing. So you'll go, great, I'm going to go search the internets for spec sheets with IEC 61000 testing listed. But you'll often come up empty-handed because products aren't usually tested to the IEC standard. They're tested to the European norm. So you'll see EN 6100-6-3 and things like this instead of IEC 6100 listed on the actual spec sheets. Do you want to speak to that?
So the good thing is that I think they're moving more away from the individual, either European norms or the CSA for Canada, DE, I think for Germany. They're moving away from these individual standards for those and just kind of migrating towards the IEC, I guess, version, although they're kind of pretty much equivalent. The way I think about it is EN 55011 is what became CISPR 11. 55022 is what became CISPR 22. I see it as CISPR 22 and CISPR 11 and CISPR 16, CISPR 32. Those are all driving what these other standards are doing now. And so it's kind of hopefully now a flow down from here's this one committee that's kind of developing them, and then the other individual countries, if they want to adopt their own individual version of the standard, they're kind of just taking and putting their own cover letter on that in essence. And so that's where if something's qualified to IEC 61000-4-4, I'm pretty confident that's going to be the same as CSA 61000-4-4. And so I don't see a whole lot of difference between those two. The best thing I see is there's harmonization going on across several of these different types of entities. Even when in IEC space and IEEE space, they're doing a lot of joint logos now or dual logo products. So you'll see IEEE IEC, I think it's 6780-323. So they've taken the IC version of the qualification standard and the IEEE version, and they've kind of merged those two things. It's kind of challenging because there's kind of different philosophies between the two. But I think the more that we move into that space, the better off we're going to be. There's even talk about the IEC 62003 document maybe at some point being combined with the IEEE P2425 document. Again, this way, there's one guidance document that's pushing things forward rather than two different standards that are over here.
Yeah, everything's moving towards a harmonization of engineering standards and regulations and stuff, right? We're just out there setting the stage for the one world government order, and it will have its pros and cons, but one pro will be that we don't have to spend as much time.
Hopefully it's not more straightforward, but yeah, I think there will always be uniqueness, I guess, to each either individual country or each individual portion of the world. And a lot of it comes down to philosophy. Again, right now, the US philosophy is we qualify to the worst case environment no matter where it's going. We want to qualify something once. We don't want to take the same widget and have it qualified 7 times because it's going to do 7 different parts of the plant. So qualify to the worst case and go with that. Whereas in the IC space, it's more, well, where's it going to? Let's not over-design this thing. Just make sure it can withstand where it's going to go into the plant.
I think we touched on it earlier, but there's the DIN. So you'll see DIN out at the front of certain of these European norms or IEC standards, and DIN is DIN. It's just code word for German. You'll run into that a lot. Another note is that 47 CFR Part 15, like 109G, is where the FCC accepts CISPR 22. So it's basically like this American regulation saying, hey, what the European people did was all right. That sounds fine. There's like theoretically like a 1 in a million chance that you could have something that is CE stamped that's not compliant with FCC Part 15, but more or less, it's almost always going to be. One other thing to note is that Europe has the same thing as the USA with respect to industrial stuff being less tough to meet than the residential. It's more stringent for residential. So yeah, get those residential versions. I've seen various manufacturers that will sell you an instrument and they also offer a CE compliant version of the same instrument. You know, they just have another ferrite bead or a different circuit board that they throw in there. And as you're going out and procuring stuff for your plant, spend the extra $50, get the CE checkbox on it.
Yeah. So one of the other things to look at is when you're trying to compare all these different standards. So like in the NRC Reg Guide or the EPRI Guide, they'll have, here's the limit if you're using FCC, here's the limit for using CISPR or IEC versions, and here's the limit for using MIL standard. And you'll see those are all be at different levels. So it's not necessarily that, oh, well, one's so much easier to pass. It's those different test levels are collected at different antenna distances. FCC is usually done at 30 meters, either 10 or 30 meters, because it's out in the middle of a field in an open area test site, or other people call it OATS. When it comes to IEC or CISPR testing, usually that's going to be at a 10-meter distance, either 10 meter or 3 meter. Could be at an OATS, open area test site, or it could be in a semi-anechoic chamber or an SAC. When you come to MIL standard testing, that's going to be at a distance of 1 meter in a semi-anechoic chamber. So that's where all these different levels are going to be different because the antenna is closer. So if the antenna is closer, that means your emissions have to be allowed to be higher because you're going to be much, much closer to that piece of equipment. Whereas when you go back to 30 meters, now the emissions have had a chance to drop off quite a bit, so your level is going to be a lot lower that you have to stay below. So understanding how all that works is a very, very important part. And the other thing you mentioned with like a CE version of a piece of equipment, a lot of times what that comes down to is either you've added on components or they've made cabling requirements. And so rather than using a certain type of cable, now we have to go to a braided cable. In Europe, most of their twisted shielded pair cables are 2 conductors with a braid around it, which are much better from an EMC standpoint, but much harder from an implementation standpoint. Whereas in the US, our twisted shielded pairs usually have 3 conductors in them, the 2 conductors for the signal, and then a ground conductor, and then a mylar shield around it. And so it's much, much easier to terminate that shield because you have this ground wire right for that. But from the EMI standpoint, it's not quite as good as the European version of the cable. It's good for 80% of the tests or 80% of the type of EMI, but there's that 20% that it reacts differently too. The understanding of that is kind of what makes that be a CE version of that system.
So all of you reactor designers in America trying to sell plants in Europe, you're going to go sit down and make your European version of the plant. Take good notes.
Yeah, well, because one of the other trends we're seeing is a lot of times in the US, and most designs are this way, they bond the shield to ground at one end only. all because they're worried about ground loops. A lot of newer designs are actually bonding the shield at both ends for lower level digital or analog type of signals. So the question becomes, well, why? Why are we doing that? When it all comes down to what they're trying to protect against and how they're trying to deal with it. But that's a whole other topic to potentially talk about.
Back to the NRC and sort of some tips for designers. A lot of these non-power reactors and advanced reactors that hope to receive the same level of scrutiny as like a research reactor because, hey, if it's good enough for a trigger, hey, my 1 megawatt microreactor that uses like the same fuel as a trigger, maybe you could just regulate us like a trigger. So there's lots of people trying to do that. And if this sounds like you or someone that you know and love, the precedent for you is NUREG 1537, Part 1. And basically, this gives copies of safety evaluation reports for 2 digital systems at trigger reactors, little upgrades there. And basically, they cite that electromagnetic interference was evaluated, but found to be not significant because of the associated safety functions and the reactor's safety case. So there's lots of good little nuggets in there that you can cite back to the NRC if you feel like your reviewer's urging you on to do more than you think is reasonable on EMC issues there. Another thing to talk through is that, and this is sort of like an equipment qualification thing in general, is that generally any type of equipment qualification, whether it's seismic or radiation or whatever, the design basis is just to prevent common cause failures from taking out like multiple systems at the same time. And so there's this distinguishment between mild and harsh, where a harsh environment is this thing that is above an anticipated operational occurrence, where you're going to have a LOCA, like large break, line break that causes your environment to change and increase drastically, and that's going to take out all your equipment. So that's a harsh environment. And there's the mild environment where it stays roughly the same all the time. Even if it is this very high radiation, very high temperature environment, it's still a mild environment because it just stays the same all the time. There's no harsh spike that's going to happen. So there is this concept in EMI land as well, where you can have a bit of a mild EMI environment versus a harsh environment where, once every few months, this pump is going to kick on right next to it and drastically change the environment that it's seeing. So any tips for people on how to credit being in a mild versus a harsh environment and different tactics for dealing with each?
So in the IC 62003 standard, we tried to help give guidance for how do you evaluate what your environment's going to be. And the big thing there, the first thing I'm going to start with is we talk about interface types there. So not necessarily where's your piece of equipment located, but what's your interface type of that piece of equipment. Because typically you would think, okay, control room, it should be a quiet environment. It's surrounded by concrete. So this should be a low noise environment from an EMI standpoint. However, that control room or that system interfaces with parts outside in the plant. And so that's where I think about, okay, what are you interfacing with? If you have a cable in the control room or a system in the control room that connects out to the Met Tower outside, that's going to be able to bring in a lot of noise into that portion of the system. That would be what I would call a harsh type of environment. Whereas if it's a control panel that's going down to the cable spreading room, okay, that's going to be a very, very mild environment because your cable goes to a very low noise environment. So a lot of it comes down to not just think about, okay, where's my system at, but what's my system connect to? If it goes down to some of the bus bars out in the plant or near where you're actually doing the electrical process, that's going to be a harsher environment than just going out somewhere in the turbine deck. So understanding where your system's going really feeds into that determination of are you light, mild, or severe. Taking a look at how is my system grounded? What's that look like from the standpoint of, am I a big piece of metal that's right here, or am I kind of off on my own? What type of shielding do you use? What type of power supply do you have? Is it a battery back power supply that you're not really going to have a lot of harmonics or a lot of power quality issues or not? So there's like 14 different criteria that you look at and evaluate when it comes to determining what's the severity of that. So again, by no means is that comprehensive. By no means has that been fully developed. There's still more work that has to be done in that, but that was kind of the first crack at trying to help with a designer or a vendor determine where am I going into the plant environment. I'm looking, I think that's Appendix B of that standard. That's probably the place I would start.
Yeah, and there's still a lot of debate about, and a lot of aspects of nuclear power plant design between the classic black and white, safety related or not safety related, and then now all these in between classifications that came out in 10 CFR 5069 and the forthcoming Part 53 and the NEI 1804 licensing modernization program, and then RITNIS back in the day, and even like PAM, post-accident monitoring. What do? Do you apply the full regulatory guide 1180 for all of these in between more important than non-safety but not safety related components? Or what do you do? Because like I've been noodling on this a lot in my life recently, and certain things like, hey, we're just going to require any of these aerospace or other standards, like just as long as it's got any amount of pedigree. If it's got a FCC report, we're just going to give it a smiley face and say that was enough. And that's more than we're doing on purely commercial stuff. Therefore, this is a sufficient and reasonable thing. What are your thoughts about what is appropriate? And I know it depends. And to me, it should depend on, well, how commercially significant is it? Because you should be doing a lot of this anyway, just for commercial reasons. But yeah,
Yes.
go ahead.
So the big one I think is in 50, I guess 5069, the recategorization of safety related systems and saying, okay, this one's safety related, but it's low consequence, I guess. And so that's where there was a push to try and say, well, we don't have to worry about EMC of that system, because if something happens to it, we're not really taking a whole lot of credit for that. And so the risk of that is not that consequential. But so that's where EMC was trying to be pushed out completely. For me, it still comes down to, okay, even if you don't care if that system performs its function necessarily, you still want to have it, but it's not critical. You still have to do emissions testing and or verify that it's not going to basically cause interference with things as you put it into the plant. That's where you would kind of treat that from an NRC regulatory standpoint. You would kind of treat that as a non-safety-ish type piece of equipment. So you at least still have to make sure that anything you're putting into the plant is not going to significantly increase the level of noise that's in the plant. And it's kind of the same when you talk about the important power production, important commercial aspects, equipment. You may only be required to do emissions testing of it, but that's where you may want to say, okay, what type of EMI do I expect to see at that point in the plant? And are there things I want to protect against? If it's an important power production system that's 120 volt DC powered, coming off the battery bank, you may not have to worry about surge testing of that, because the chance you're going to see a surge, not that high. But electrical fast transients, that you probably do want to test against, because those are everywhere in the plant. So making sure that you put the pedigree in your system that is necessary for your environment you're going into. If you have the ability to ascertain what that environment looks like to a fairly high degree and you can design against it, you may have to do any testing. Whereas if you can't, that's when you have to be a little bit more cautious.
This also ties back into, I think it's general design criterion for 10 CFR 50 Appendix A and the equivalent principal design criteria that advanced reactors use, right? It's just like, hey, make sure your stuff that's important can withstand its environment.
Well, and that's always still one of the big debates of when you say, okay, be able to withstand the environment, does the electromagnetic environment play into that? Or is that just temperature, humidity, radiation environment?
Which side of the debate are you on? Because it depends on whatever I feel like.
I interpret it as the electromagnetic environment is certainly part of the environment. So that's my vote.
Sure. The guy that sells EMC testing definitely thinks it is. I tend to think so too. I mean, Regulatory Guide 1180 itself cites 10 CFR 5049, and I think it also cites GDC 4. I'd have to double check, but there's also stuff implicitly pointing to it is. So do it. It's good for you. It's like eating vegetables. Make sure you're designed as EMI. So, I mean, we've spent all day talking about electromagnetic interference, but what about radio frequency interference? Can you speak to what is the difference between these two things?
So I think of electromagnetic interference as everything. It covers all frequencies, all types of noise. Radio frequency interference is basically higher frequencies. So it's things that are higher frequencies that can either be radiated through the air, which we think about, or conducted on cables, but they're going to basically be higher frequencies. So EMI is everything. RFI is kind of a subset of EMI. So that's how I normally think about it. I use the terms interchangeably for the most part. Sometimes I'll write down EMI. Sometimes I'll put down EMI RFI. I just try to make sure I'm consistent with that, with how I'm doing it. Usually if I'm trying to bring wireless into the conversation, I'll add that EMI RFI portion into it, but I treat them as two and the same things.
Yeah, I think that you're always good to just say EMI, because that's the full spectrum. And then it's almost like a completeness and accuracy thing that some Poindexter will just be like, but you didn't mention RFI, and our reg guides say RFI too. And then you'll say, fine, I'll say RFI here too. But it's just this narrow portion of the span.
Because if you bring EMC back into it, you want EMC, you don't want EMI. So
yeah, that's true. Yeah, EMC is not a bad thing. That's the good thing you want. Very good. All our listeners have probably experienced EMC and just not known it. For example, and I don't know, I'll like go through a list and say, you can say whether this is EMC or just me being an idiot in some other physics phenomena. But yeah, it's like I'm sitting there next to my microwave and I'm scrolling on my smartphone, and then I microwave my pizza rolls. And as soon as the microwave kicks on, my internet goes out on my phone. Is this
Yeah,
EMI?
so that would be the EMI. So the microwave puts off noise in the 2.4 gigahertz range. Because I remember I was doing testing in a plant one time, mapping for as they wanted to implement Wi-Fi and other systems. And as we were mapping, one of the operators was warming up their lunch, and so we saw this big, huge spike come in the 2.4 range. That would definitely be EMI. Now, unfortunately, nowadays most of the Wi-Fi systems, they're either going to work in the 2.4 range or they'll jump up to 5 gigahertz range. And they do a pretty good job about hopping around and figuring out, okay, where do I want to be at? So they kind of avoid that as best they can. But yeah, that's definitely EMI. Well, actually, maybe it's RFI. We may call that RFI.
Oh, hey, there you go. So, there's things that leave the factory and they're like, good to go for EMI, but then I like drop it during shipping and, things get jostled off the board or whatever, ferrite bead falls off, and then suddenly you install it in the plant and things go wrong. This is a potential failure mechanism. So, like, I've got a cell phone charger and my kids have thrown it around on the ground like 100 times, and suddenly, like, I plug it in and it still charges, but like I hear this faint buzz as my phone's charging. Is this EMI or some other physics issue?
I would say most likely, yes. You've changed the configuration of that, probably changed the shielding of that maybe a little bit. So now you may be putting out more noise than what you expect to see. Now, the good thing is since it's audio, it's going to be fairly low frequency that you're hearing, hopefully. So from EMI standpoint, it shouldn't interfere with a whole lot of things. But yeah, it's one of the similar things of when you qualify a piece of equipment, do you qualify the piece of equipment before it goes through all the environmental testing and it's been aged and degraded? Or do you do at the end of all that testing? Most everybody will actually probably use a separate sample and test a brand new system for the EMC qualification testing. But there's something to be said to say, well, maybe we should actually subject the one that's gone through aging to the EMC qualification testing, because that's going to tell you how it performs towards the end of its life. And then you have the salesman who would say, well, no, you got to test at the beginning and you have tests at the end, and maybe even in between, because it could change as you go through. But that's one of those Pandora boxes. We're kind of keeping that lid closed for right now, not really asking the question about when do you actually subject it to EMC qualification testing. But that question's out there because as shields degrade, as capacitors degrade, you're going to change your EMC performance.
Yeah, and please do keep that box closed, because I, as the designer that would be your customer, would always be like, no, it's like reasonable enough assurance. Come on, man. Like, be a bro.
Help me out here, man.
That actually brings up a different topic I wanted to talk to you about, and that is maybe you could do EMI RFI testing and say it's non-destructive and like save yourself from having to burn a destructive test. And like essentially you build a prototype of this pump or this instrument or whatever. It might be like a $50,000 instrument, and then you're just going to zap it with stuff. And then sometimes it's just a matter of there's one little component in that $50,000 specimen that I would have to like refurbish and then say it's good to go, versus just always saying it was a destructive test and it must be scrapped and used for training or something and never see the glory of use in the plant. So what is your thoughts on salvaging and whether it's destructive or not?
Okay, so a majority of the EMC tests are non-destructive. I consider them non-destructive. The destructive tests are going to be the surge withstand capability tests. So the combination wave surge, the ring wave surge, those are two destructive tests, potentially destructive. Electrostatic discharge is another one that is usually very destructive. Electrical fast transients, I normally don't see that as being destructive, but it has potential to degrade capacitors. So you could treat that as potentially destructive. So you have two camps. One is whatever's gone through EMC qualification testing, I don't want to put in the plant. So you basically make your own sacrificial sample that's going to go through qualification testing, which is a completely valid point, can be used. Another approach is saying, well, yeah, but if I build this system and I build this other system, if I say they're the same, were they wired the same? Are the components the same? So is it going to perform the same from an EMC standpoint? So in nuclear space, we usually just qualify one and say, well, that's representative. In other industries, if they have thousands of components, they'll pull out 10 or 100. They'll get some sampling and say, okay, these samples all pass, or a certain number of the samples pass, therefore likely all of them pass. So that's where if you say, well, I'm just going to build one sacrificial lamb and subject that to EMC qualification testing, well, it may or may not match how you actually designed or built your second system. It's another challenge with saying, well, I qualified this system 5 years ago. I'm using the exact same parts, components for the most part, so it's also qualified. That doesn't necessarily hold water. Again, you're always taking a risk by doing that approach. Now, do I think that you can ever do that approach? No, I think you can. We've written justifications and evaluations for saying, well, we changed this one component. Is our EMC qualification testing still valid? For me, for the most part, if you subjected a piece of equipment to surge testing, you at least probably want to change out the surge suppression that's within that system. So every system you put in the plant, if you're going to subject it to surge testing, you should put surge suppression into it. So just take that out and put new in before you put it in the plant, is kind of my approach with addressing that. So it's not a full-scale replacement of everything, but at least replace what you think would have been impacted by the surge testing.
Yeah, this flows into a different point, a historical point, and I will look up the reference, but there's a certain reg guide out there, or like some new reg out on the books, where the NRC essentially for all equipment qualification related testing said, hey, if you test 10 different components in a lot, 10 specimens, and one of the 10 fails, we're going to assume that all 10 fail and everything fails. And so essentially, like, there is this punishment mechanism where if you try to be a good little boy and do a larger sample set, it's just opening yourself up to vulnerability. You will get no credit for partial lot passing. So yeah, it's something where the NRC could update that stance, and then people could take these other approaches more easily. And that's something where, especially when people are like in the reliability estimating land, probabilistic risk assessment land, and all these risk-based regulatory platforms, that's sort of batch testing that they want to do. But there is still this thing on the book that makes you not want to do that in equipment qualification land. And also you could say we as an industry need to like make the NRC get their act together and like change this stance. But that would be essentially forcing more burden and expense on you as the industry, because it's like, hey, presently we just have to test one and it either does or it doesn't pass. Why would I want to like force myself to test 10? And so let's just all keep the status quo, choose other battles to fight. Chad, can you teach us how to design a military shield for an exoskeleton suit whose heads-up display can handle the electromagnetic interference induced by transient surges of plasma rifle shots? It needs to also simultaneously emit a small enough electromagnetic interference so as to prevent damaging a safety significant to the universe co-located Cortana AI assistance memory.
I have my prototype right there. It's been under development for a few years, but yeah, we're close to a breakthrough, so we can easily have that going in the next year or so.
Nice.
So sometimes I can wear that around plants if I want to, make sure that I'm not causing interference with things. I can wear that around.
That's great radiation shielding too if you need to go to a high rad zone.
Exactly. Too. Yep. So it was something that my brother and sister got it for me as a wedding gift because they wanted to really annoy, I think, my wife at the time. So it was at home. It wasn't allowed to be at home anymore. So we actually, remember the Harlem Shake craze from 10 years ago?
Oh, yeah.
So we did a competition here of our building versus the adjacent building. So I wore that during that video. And then it's stayed ever since. And now it's a staple in my office.
The nuclear industry is always living in the past. And that's a past I'd be fine going back to, the Harlem Shake. Earlier, we talked about modeling EMI with software in your plant. And this is a thing that is generally not actually done. But for the potential of if some advanced reactors out there that thinks they actually do have their rebar spacing close enough known to make this a useful practice. You know, besides COMSOL, I think that ANSYS has different EMI capabilities and they've got NQA1 paperwork, and everyone in the world uses ANSYS to do everything in nuclear and every other ecosystem in engineering land. But one that's flown under the radar that has recently come out is the Siemens has a new, essentially 3D modeling software. It's called Simcenter 3D Engineering Desktop and Simcenter Nastran 2306. And they've got an electromagnetism modeling program in there. And they have also attained compliance with and have a nuclear quality assurance NQA1 2015. I'm not sure of the price difference between these two, but anyway, now people know that this is a alternative option. If you thought that ANSYS had a monopoly, other things exist for nuclear analysis.
I expect that a lot more of the advanced reactors will all be kind of designed from the get-go. So if you already have a lot of those drawings or a lot of those models there, it's going to be a lot easier than some of the old facilities, it was all just paper. So having to go back and trying to figure out, okay, what do we actually build, I think is where their challenge is. So yeah, I could definitely see it being more applicable for a lot of the newer designs.
And you're telling me about this horror story battle scar from your career where you had a quiet system that you installed next to a quiet system, and then there were still EMI RFI issues or something like that. Do you want to speak to that one?
Yeah, so in essence, what happened is a plant had just a digital meter. So they were going from an old analog meter to a digital meter. So the old analog meter just took in a 120 volt AC signal. So basically, it was fed a signal that it just indicated. The digital one was powered by 125 volts DC and then had the same 120 volt AC signal coming into it and just displayed whatever the signal was associated with the diesel generator. When they upgraded the system, they put this new digital one in and they said, oh, it's just a digital meter. We're not testing for EMI. It's fine. So went in without any qualification testing being done. When they put it in, it supposedly interfered with an adjacent analog meter. So they said, okay, we're going to take this one out and go back to the old meter for now. And that's when they send us the new meter to say, hey, EMC this thing. Make sure it's good. And so we did a bunch of emissions testing of it to say, okay, maybe this thing just caused a bunch of noise that interfered with the adjacent one. So we went through and we did the traditional emissions testing on it. I mean, it was quiet as anything. Basically made almost no noise. So then we did a bunch of other types of tests to try and find noise for this thing. We powered it from I'm going to call it a soft 125 volt DC source. We actually tested the 120 AC signal to it, tried a bunch of different things to make it be noisy and couldn't do it. So what had turned out to be the case is when they installed the new meter, they ran a new 125 volt DC line to the meter. That DC line went through the control panel in the control room, or the control board, I should say. So they added this new 125 volt DC line. Well, the plant's 125 volt DC line was noisy. And that's what was causing interference with the existing lines. So the new meter had really nothing to do with it. It's just how they had installed that new 125 volt DC line. So just because you put a qualified system into the plant doesn't mean you're not going to have issues because, well, what's actually feeding that new system and how are you routing cables in the plant? Like I say, 80% of EMI issues that I see, whether it's from a plant level or from just individual system level, come down to cable routing and not having enough cable separation.
Yeah, definitely. Some of this always overlooked. And hey, I thought Jerry was doing it. Oh, well, Jerry thought you were doing it. All this tracking where cables go from the outset of the design so that you have enough penetrations and that you don't run out of space to avoid the co-located single point vulnerability for the separations. Some people use the software called Edison to do that, and there's other softwares for cable management stuff.
I often tell vendors, make sure you have a wiring diagram for how do you want a system wired up. Not just, hey, what points go to where, but how do you actually physically want that wire routed? Because oftentimes they will design a panel and send it out to a fabricator. And so the fabricator will be the one actually doing the wiring of it. And again, all they do is wire point A to point B. They don't really think about, well, where is that wire going? So like I say, I always tell vendors, hey, tell them how to wire it up. And it's the same at the plant level, at utility level. Make sure you have a wiring guidance document that says, as you implement a system, how do you wire it up? Because even in the case of this one, so we identified that, hey, it's probably the 125 volt DC wiring that's your issue. So have them install it in this manner, route it this way. So they gave that to the maintenance crew. The maintenance crew went out there, did their own thing, didn't really follow the directions. So we went there and did a walk down and said, well, no, we wanted it over here, not there. They're like, yeah, it doesn't matter. I was like, yeah, it actually does matter. So having those things in place and then having the training to show people why it matters is really what it comes down to. And that's where, again, where when I do training, I do demonstrations. I want people to see what's actually is going on rather than just, well, trust me when I tell you it's true.
Yeah, that works with technicians and workers in the field as well as it works for your kids, right?
Exactly. Exactly.
Why do I have to be home before 10 p.m., Dad? Just
Yep.
trust me. Bad stuff happens after 10.
Yeah.
We'll point people to the appendices and different EPRI guides that are free and publicly available. You can download on their website that will sort of walk you through both how to do a survey in the field and also just how to troubleshoot EMI RFI in the field. Those are really great resources, and we'll point you to the right appendix and page number. Another good resource to point people to is that there's a guy named John Livingston who's got a website called nuclearelectricalengineer.com, I think it is. We'll put in the show notes, but he's got some different EMI RFI training videos, including one that's geared towards how do you look up reports on the FCC's website and essentially take credit for them. It's like a 10-year-old video. I'm not sure if the FCC has updated their website and made his video irrelevant now, but I think that it's still valid and people can go check it out.
Yeah. For the most part, it is. Yep.
Yeah.
The government doesn't change that quickly.
Yeah, that's right. I sort of wanted to talk a little bit about the cost of EMC testing. And so, independent of me ever asking you anything, Chad, and just from having sourced 20 different quotes for EMC testing on like 100 different widgets in my career, the cost of EMC testing I've seen generally range between like $10,000 or $100,000 for a campaign, with the median price sort of coming in at like 35 grand per component to do like a reg guide 1180 nuclear quality assurance testing campaign. And that is like a very wide range, right? $10,000 versus $100,000. And this is not including the cost of the actual test samples and components that you are providing them to go zap to death. But I think that like a reason for the cost range is that this is sort of firm fixed price versus T&M sorts of arrangements where, hey, we vow to do all this testing, and like as a line item, we're just saying $100,000 and we'll take on all risk if it fails and we'll troubleshoot it. Versus like at that $10,000 price, it's like, we're just here, man. We're just zapping it. And if you want us to try to troubleshoot it for you, that'll be an extra $300 an hour and no guarantees sorts of stuff. And so this is like the ballpark of a range of pricing. I don't know. Is there anything you would want to speak to in pricing, or just leave it there?
No, so a couple different things, I guess, feed into that. One is when it comes to qualification of equipment, whether it's just emissions, which normally would take around 3 days to perform on a system, or if you're doing the full-blown emissions and immunity, which can take 2 weeks, will play into a lot of that. A lot of times we get asked the question, well, why is it that this power supply qualification costs the same as this whole cabinet qualification? That one's a tenth of the size, so it should be a tenth of the price. When in reality, it's about the same amount of testing in a lot of cases. So that's where size really doesn't matter, I guess, in that form and fashion. Just because it's a small little widget doesn't mean it's not going to, I guess, cost the same to qualify as a bigger cabinet. Now, there is some addition of, if there's a lot of I/O cables, if there's redundant power cables, then that's going to feed into how long is the testing actually going to take. Some systems may take 4 weeks to qualify, because if there's 3 power inputs, you have to surge each input individually. You have to do all these different tests on each cable that are in there. If your system has 300 I/O cables, we don't normally qualify 300 cables. We'll have a representative sample that are there, but the extent of that representative sample will feed into, well, how long is this actually going to take? It's kind of the same with qualifying something in the laboratory versus at your vendor's facility, because now you have to have a mobile test lab to go and actually do the testing on site. And so there's a lot of things, I guess, that feed into where that price range or why that price range is there. But yeah, the biggest one is just whether it's just emissions or emissions and immunity, that's going to be the biggest driver. And then the second biggest driver is going to be the number of I/O cables, number of power cables of that system. But my general ballpark is, if it's just emissions, about 3 days. If it's immunity, roughly 2 weeks for a small system.
Yeah, just a shameless plug. I've always found AMS to be the best value proposition in terms of the quality of a person and the quality of a report you're getting versus the price. So yeah, everyone should always choose Chad and AMS for all things, in my personal opinion.
Well, I appreciate that.
Because yeah, it's like you're paying for schedule too, right? If you get someone that's going to be screwing it up and it's their first rodeo, or even just their 7th rodeo, compared to like you guys have been to 1,000 rodeos,
Yep.
You can do it a lot faster and time's money.
Yeah, well,
in terms of troubleshooting, especially.
Yeah, there's definitely times where we've gone to 24/7 coverage just to get systems tested to meet customers' deadlines. But one of the big things is, and this is what we take pride on ourselves with, is most test labs, they're a volume test lab. So they want something in, they want it back out. They want it in, they want it back out. So once your system fails, they're like, nope, get out the door, because you had a 2-week time frame. We tested in 2 weeks. We don't care that you fail. You got to take it, go redesign it, and come back. Whereas I don't like to let something leave here fail. Whether we have to troubleshoot it and or we have to come up with some justification for why it's okay, we want to lead the customer with the, hey, here's your report that says why this is okay to install. Whether that includes, hey, you had to add all these different components, which will be at an extra cost for troubleshooting, but you have to add these extra components, or here's your justification for why it's okay. You're going to install in conduit, or you're going to keep the doors closed, or you're going to maintain this separation distance, whatever you're going to do. So like I said, we want to give them what they need rather than just, well, here's your system, bring it back to us in 2 months. Once you redesign it, we'll test it again. Oh, it failed again? Okay, go away, come back in 2 weeks and test it again.
Yeah, there's people that believe in the nuclear promise, and you're a nuclear company trying to do something. I'm just going to bend over backwards to help you realize the nuclear dream. And AMS is certainly in that camp. And so if you're a nuclear customer, you want to be partnering with people who have the same vision and are as committed as you to this glorious dream. But the other big difference between some third-party electrical engineering EMC providing service, there's obviously dozens because nuclear is not the only industry that cares about EMC. But when you go to a nuclear specific qualification company such as AMS, you understand IEEE 344 and like seismic considerations and all these other things where you understand that like there's these certain constraints about what you can do and what you can modify in a system that's already undergone aging and 7 other things. You know the amount of wiggle room that you have to work in without invalidating all those more expensive qualifications. And that is worth a ton. The fact that you have that knowledge and can work within that framework that frankly you are not going to get at a different EMC qualification company. Another plug there. And also, yeah, I've never been change ordered to death by AMS, but other people, if your component fails, it's like they just start licking their lips and are just like, all right, now we've got the customer right where we want them. But yeah, AMS is just a very high integrity company. So
I appreciate that.
Another resource that we'll post on our website for users that register on nucleartalentboost.com is going to be a little example cookbook of like how to write your specification to make it actionable and economical and also meeting regulations. So I know that EPRI in one of their guides, the revision 5 of the 10232, I forget what the one.
Yeah, 102323.
Yeah, they have a similar, here's like a dummy spec, but we've got our own version because it's a brave new world. And what do you do for the non-safety related special treatment stuff? So we'll have our little penned up ideas there, and that'll be a neat little thing for people to see. And yeah, are there any closing statements that you have?
The biggest closing statement is EMC is seen as this black magic. Nobody understands it, so keep it away from me. It's not that difficult. Even I can do it. There's simple things that can be done where you can address most of these issues. And so, like I say, don't be afraid of it. But more than that, thank you for spending the time with me to sit down and talk about it. I always enjoy talking about this stuff.
Yeah, no, I'm very pleased to give people a platform to speak about the topics near and dear to their heart so that the other 50 souls that actually really are super gung-ho about this can find each other.
Yep.
And to grow the pool of people that should care about this, because INC engineering is a very in-demand thing. We're trying to build the talent pool for it. And even within the current INC crop, there's just so many people that are totally ignorant or know enough to be dangerous, but are actually sort of clueless and running you down the wrong rabbit holes on EMCs. So I think a lot of what you've shared just now and what we have available at nucleartalentboost.com for the extra portions of the interview we didn't make immediately public. I mean, it's all still free. You just have to register as a user. Yeah, I think it's going to open a lot of eyes, help people execute their current jobs a lot better, and make themselves more valuable to future employers. Whether you want to be looking at trapezoidal waveforms on an oscilloscope, or whether you just want to know a few different paragraphs of text to put in your design spec to make your spec suck less at EMC and be actually biddable and qualifiable by your vendor on a good time frame, or honestly, you really need to go take Chad's full multiple day training and get your hands on all of these MNTE and different equipment to be doing this stuff. He's saved the best for there. Nothing replaces actually having the master sitting there touching widgets and transferring his knowledge to you. So it's in the winter, it's in Florida, it's going to be beautiful.
Yep.
Everybody please go register there.
Yeah, and as you said, so EMC, we have the coolest toys.
Yeah, that's right. Do you have one of the hot shots?
The little ESD guns, be able to zap things with. We have Van de Graaff generator. We have all kinds of things.
Oh man, go pretend to be Tesla or something.
Exactly.
So beautiful.
We hope you enjoyed the show. We're helping solve the energy crisis for our children and the world by addressing the nuclear talent shortage. Please help us by liking, sharing, and subscribing, registering on nucleartalentboost.com, and telling your human resources and procurement departments you'd like to work with nucleartalentscout.com for all your staffing needs.